Jonathan showed this figure earlier, showing the places around Antarctica and Greenland that are melting the fastest today. It's the places that are red. And you can see that they're around the edges of the big ice sheets. They're not in the center of these continents. In a moment, we're going to talk about how Greenland and Antarctica are really fundamentally different, and not just how Greenland and Antarctica and their ice sheets are fundamentally different, and how they will respond differently to future warming, like the warming that Tim just talked about, but how this West Antarctic piece of the ice sheet is very different from the East Antarctic piece. Now remember, there's about 7.3 meters of ice equivalent sea level rise locked up in the ice sheet on Greenland, about 4 meters, as Jonathan said, on West Antarctica, and a little more than 50 meters of ice locked up on the East Antarctic ice sheet and continent. So this is great because I'm going to basically repeat little pieces of all the previous talks. So you'll hear some of the key concepts sort of woven together and wrapped hopefully into some sort of coherent picture that will sort of drive what I'm doing, which is trying to include these processes in physical models. They're numerical models. They are basically scientific software, computer code that runs on supercomputers to do two things: to try to simulate the modern system, because if we can simulate the modern system in a computer, it means that we're beginning to learn the physics of how that system works. And that's wonderful. Then we want to test those models, and we can't really test those models against the future because, right, the future is data poor. We don't have a lot of data from the future. So we have to turn to the past. So, I have, I think, the greatest job in the world because I get to work with people like Tim Naish, who produce records of what the past was like, that I need to test my models. I rely on the data of the current system that are coming from people like Jonathan and from Steve, because those are inputs that go into these models and they help us build the models for the present day. And then we take these sophisticated models and we apply future possible scenarios of greenhouse increase. So we can apply scenarios where we do just what Tim suggested we need to do. Very, very aggressive reduction in emissions within the next century. And we can see how the climate system responds and how the ice sheets respond. We can also take the model and say, okay, we're going to go business as usual. We're going to burn, baby, burn. We're going to burn all of it. 5,000 gigatons in the next 2 centuries of carbon. And we can see what the models do. So this is the first important process that has been sort of an enlightening thing for the glaciological community that Steve touched on, that is one of the critical things in these models that we are beginning to use to try to say something about the future. And it goes back to this difference now between West Antarctica and East Antarctica. This is another map of the bathymetry of the continent, the elevation of the land surface. And everything in this map that's in blue is below sea level, and everything that's in red is above sea level. And of course, the big ice sheet is sitting on top of that bed. And again, you can see that West Antarctica is sitting mostly on bedrock that's well below sea level, more than 1 kilometer in some places below sea level, hundreds of meters. So the ice sheet that's sitting on this part of the continent is essentially sitting in a bowl, and it's bathed in ocean water. And as we learned from Steve, it's sitting in a bowl of ocean water that's beginning to warm. Okay, the East Antarctic ice sheet is mostly sitting on continent that is well above sea level. So it's not really interacting directly with the ocean, except in a couple of important places. Here, this deep subglacial basin that's well below sea level, and you can see another one right here. Now, why in some ways this part of the continent is really, really important and really interesting is that the thickest part of the ice sheet happens to sit in this sector of Antarctica, okay, which is sitting on bedrock that's well below sea level. So it turns out that the amount of ice that is in these basins, if all of that ice that's in blue here and here were to go into the ocean, sea level would rise about 20 meters, as opposed to the ice on West Antarctica, and that's sitting on this bedrock below sea level. If this were all to melt, as Jonathan noted, sea level would rise about 4 meters. So, interesting. There are subglacial basins with an enormous amount of ice sitting on them. And could they be vulnerable in the future? Tim showed us that he has geological evidence to suggest that this part of the continent has disappeared in the past when the world was just a little bit warmer than today. This is a really important question. Could this part of the continent also be vulnerable to a little bit of warming? So we're going to go back to this nice picture that Steve showed us of an ice sheet with a grounding line. The ice is flowing from the continent over here out into the ocean. And as it reaches the ocean, it doesn't instantly melt because the ocean's pretty cold. And it's able to sort of stick a snout out into the ocean. And that's this nice, thick, floating ice shelf. That's the grounding line where the ice sheet is beginning to float. So when you go toward the ocean, past the grounding line, you become an ice shelf. You're no longer the ice sheet. Here, in many places around the continent where we have the ice flowing out into the ocean, this grounding line is, roughly, let's say, 1 kilometer thick. And then as you move away from the grounding line, the ice shelves typically thin to maybe a couple 100 meters thick. Okay? So here's the ocean that, as Steve told us, has the potential, and in some places this is actually really happening today, for water a few degrees above the melt point of ice is getting up into these cavities under these ice shelves and is beginning to melt and thin these ice shelves in places around the continent. Now, why that's really critical is, again, as Steve mentioned this important word, that the ice shelves are slowing down, they're buttressing, holding back the flow of ice that's coming off the continent. It's a really important point here. Okay, so about 40 years ago, a really, really clever, intuitive glacial geologist thought about this particular issue, and not quite the same way that a real glaciologist or a ice sheet modeler thinks about it, but that person, John Mercer, and some other important glaciologists from way back in the day, Hans Wertmann, one of them, and some very recent work by a very sharp applied mathematician, Christian Schoof, we're sort of all leaning toward an understanding of something we call marine ice sheet instability. This is that tipping point instability that Steve noted, and it's related to what I just spent 6 minutes telling you about. Here's that ice sheet again. This is just another picture of the big, thick ice sheet, and there's the grounding line, and there's that little snout, that ice shelf sticking out that's helping to slow down the flow of ice out into the ocean. Okay, so if you could imagine, the ocean out here warms, and that little ice shelf begins to thin, or maybe even disappear completely. You could have an increase in that term Q, which is just the flux, the flow of ice out through the grounding line. So if we lose the ice shelf, we get more ice flowing out into the ocean, and the surface of the ice sheet will drop because it's losing mass. And if the surface of the ice sheet drops because it's thinning, it will no longer stick to its bed here. It will start to float. So the grounding line will lift off the bed, and if it lifts off the bed, that means that it will have to retreat. So if it retreats, do you all see the difference between this grounding line, that dashed red line, and this one? I hope you can all see that the dashed line in the bottom diagram is thicker. It's thicker here because it's retreated, and this is the key, is that it's retreating on bedrock that, as Jonathan noted, in many places is sloping down into the continent, toward the continent, not down toward the ocean. It's on what we call a reverse sloped bed. Okay, so the grounding line has just gotten thicker, which means it turns out that we can actually start to pump more ice through the grounding line. And it's really interesting. The amount of ice that can flow through the grounding line is related to how thick the grounding line is. That's pretty intuitive, but it's an exponential relationship. So if the grounding line gets just a little thicker as it starts to retreat, you start pumping an exponentially greater amount of ice out of the ice sheet. And that, as you could see, will just lead to a runaway retreat, where once that grounding line starts to come back onto that reverse slope bed, the system just takes off. And that's this so-called marine ice sheet instability. And we have now incorporated those sorts of physics into ice sheet models. This is the West Antarctic ice sheet, and all that we're doing in this model is warming the ocean temperatures under those ice shelves by 2 degrees Celsius. And as soon as we do that, the ice shelves that are in pink, so just to get your head around this, here are the ice shelves. They're thinning. We're losing the buttressing, and the ice sheet retreats back into the bowl of West Antarctica, especially in places where the bed is reverse slope. So this is the marine ice sheet instability as we see it in our numerical models, okay, which is pretty exciting. Now it's interesting, the retreat of the ice sheet, right? The retreat of the ice sheet took 3,000 years in this simulation, okay? And this was published in a paper in 2009, and when this came out, I thought, oh, the press is going to be all over this. This is, really exciting. It's important for our future. And the headlines in some of the newspapers around the world were slow motion meltdown of the Antarctic ice sheet. So that was a bit of a surprise. Okay, things get really interesting here in a minute. Here's that map again of bathymetry. The blues are the land below sea level. Again, these deep basins. This is the thickness, just to get a feeling for this. This is the thickness of the ice in those subglacial basins. And again, this is the part of the continent. These are the subglacial basins with the really dangerous long-term future potential sea level rise that we're worried about. So we take these models, and one thing, just so that you know how we might drive these models, what you tell them about future climate, we use the state-of-the-art climate models that we use to do these future projections of what climate is going to be like. And these models include, for the atmosphere, basically it's a global scale weather model with the same physics that when you woke up this morning and watched your favorite broadcast meteorologist give you the forecast, that information came from a model like this, except this one is global in scale. These models include ocean circulation that Steve showed you, and we can take these models, we run them out into the future. High CO2 future, modest CO2 increase future, and we see what happens. Then we take this climate, the temperature, the snowfall over Antarctica, the warming of the ocean around Antarctica, and we run these ice sheet models. The ice sheet models are doing a really great job nowadays, the current generation, of even simulating the flow, the velocity of ice, the speed of ice as it flows. The fastest flowing ice in the models is very much in the same place that we see from observations. This is how we use the data from Jonathan and the kinds of work that he does, and we compare with our modeling. So this is how the community sort of works together, even though we're all bringing different parts of the puzzle to the table. So this is what the models have been telling us about the future. This is what Tim just told us, and we can reiterate. Here are two possible futures. This is a very aggressive greenhouse gas reduction scenario where in around 2050 we go close to zero emissions. Probably not going to happen. This is business as usual. This is our sort of worst case scenario of where greenhouse gases are going in the future. It's essentially business as usual until we blow through about 5,000 gigatons of fossil fuel. And the difference is, of quite staggering when we think about sea level rise. And as Tim said, the current sort of accepted community estimate in terms of the high end of where sea level might go over the next century, so at the year 2100, is roughly a meter. So at the high end of uncertainty estimates, about 1 meter higher than today. That would be devastating, right? Every time there's a storm surge, a coastal hurricane, century timescale events, flood events become sort of an annual thing in a lot of coastal cities around the world. Okay, the best case scenario, maybe we're only going to see about a half meter of sea level rise over the next century. Okay, the models up to today have been sort of neglecting some physics that might be really important. This is a really important event that happened in 2002. This is a satellite image of a piece of the Antarctic Peninsula. This is an ice shelf roughly the size of the American state of Rhode Island that broke apart over the course of about 3 weeks. And just before it broke up, and this is an image of it actually disintegrating, it was covered with meltwater because the atmospheric temperatures were warm enough in the summer to make surface melt on that ice shelf. So the ice shelf was melting from below, from the ocean processes Steve talked about, but in the summertime there was so much meltwater on the ice that every place there was a crevasse, the water went into the crevasse and helped break up the ice shelf. The ice shelf was 220 meters thick on average, and it broke up in a matter of weeks. And as soon as it disappeared, you can see these outlet glaciers that used to be buttressed by the ice shelf. They sped up by about a factor of 4. Okay? Now this just is a little piece of the Antarctic ice sheet up on the peninsula. Okay, the other thing that happened is if we look at this glacier, this is the Crane Glacier that used to be buttressed by that ice shelf. This is what it looks like today. Its ice shelf is gone, and it has in front of it now, there's no ice shelf. This is just all broken up icebergs. This is the grounding line it's a naked grounding line. It has no protective ice shelf, and it is collapsing. It's disintegrating. This cliff is so high that the ice can't hold itself up because ice just isn't that strong, and it's physically just breaking off and retreating. These kinds of physics, haven't been in the models until just recently. When we put these kinds of physics into these models, we get the kind of sea level rise. This is an important point in the Pliocene that Tim talked about, 20 meters of sea level rise for the first time. So some new physics are still being thought about and put in these models that for the first time are doing a better job simulating past sea level rise. So now let's see what happens when we put these state-of-the-art new models that are doing a better job with the paleo matching to the future. And that's where we'll end, is looking at the scenarios. Okay, the first thing I want you to all sort of a take-home point tonight is that, remember, we have these possible futures. We have aggressive reductions in greenhouse emissions, or we have business as usual sorts of worlds. Okay, if we look at sort of the best case scenario with aggressive reductions, these are maps of temperature, surface air temperature, like in this room, over Antarctica in Antarctica's summer. And anything, you don't need to know the details, anything that is in yellow is above 0. So any place you see there being a little bit of yellow means that it's above freezing in the summer, and that can make surface melt on the ice shelves. And we know from experience, from what happened to the Larsen ice shelf in 2002, that surface melt on the ice shelves can make them potentially vulnerable, weak, and they can break up. At high levels of CO2, where we are headed in the coming century, in a business as usual scenario, you can see that all of the major ice shelves, the huge Ross ice shelf, the Filchner and the Ronne ice shelf system, the ice shelf that's here in the Amory ice shelf over here in Prids Bay, they're all going to be many degrees above freezing in the summer, and they will be covered with meltwater. Okay, that's the world we're heading into. So when we take all of these things into account, we can look to see what happens to the ice sheet in sort of a more modest warm summer world and a really warm summer world. So we take climate from sophisticated climate models, low CO2, high CO2 scenarios. That tells us what's going to happen to the surface of the ice sheet. Then we take ocean models, like the models that Steve uses in his work is important in testing, and we look at what the ocean is going to do around Antarctica for a low CO2 future, a medium CO2 future, a high CO2 future. We combine the ocean warming, the atmospheric warming, and then we look at these new state-of-the-art ice sheet models and see what they do in the future. And this is what they do. Okay, so this is the worst case scenario, where it's basically business as usual. And the model simulation is going to start, I'm going to back up. We're going to start in the year 1950, so you have a little time to see what's happening. Up here will be a timestamp. This is in years, like CE, Common Era, so this is 1950. And I'm going to run the model for 500 years. You can see these light blue colors. So all of the colors are basically just the thickness of the ice sheet. The light blues in the embayments here are the ice shelves. And you can see back in 1950, they're nice and big and thick and healthy. And we're going to see what happens to the ice sheet. Now, the first place I want you to watch when I click the button is keep your eye on this part of Antarctica. Remember, Jonathan showed us this is where the ice sheet is beginning to respond to warming today. This is where the action is in the Amundsen Sea embayment, right around here, and the outlet glaciers that are flowing out into the ocean right here. And you can see that at the beginning of the simulation, I think you can all see there's a little patch of light blue in there. Those ice streams, those outlet glaciers flowing out into this part of Antarctica have an ice shelf in 1950. And you're going to see right when we get to about 2010 in the model, the last pieces of that ice shelf are gone because the ocean's too warm for them and the air's starting to get too warm. And as soon as those ice shelves are gone, you're going to see a big retreat in this part of the ice sheet. And then that's going to get boring to watch because it's going to go away fast. And then I want you to start to look and watch this ice shelf. The massive Ross ice shelf, about the size of France and 1,000 meters thick near its edges, is going to be gone. And keep your eye on, of course, on the timestamp to see when that happens. So here we go. Okay, so gone, ice shelves are gone, 2010. The Ross ice shelf goes. So this is that marine ice sheet instability in action, and we're exposing those big, tall cliffs in places that don't have a protective ice shelf anymore, and those cliffs are just collapsing. And as the model keeps running, this is the year 2350, so a few hundred years in the future, we're actually getting that retreat into those two deep basins in East Antarctica where the thickest part of the ice sheet is. Okay? So this is what the projections look like in terms of the total amount of sea level. This is that worst case scenario, and it's several meters in the next 100 years, and maybe as high as 10 meters or more in the next 500 years. Okay, now that sounds dire, and it would be terrible for me to just like, okay, the talks are over and we're all doomed, right? The good news, and this is the way I look at this, is that if you look at, right, the more modest increases in greenhouse gases, so this would require, right, huge, enormous global environmental cooperation and policy making for this kind of reduction in greenhouse emissions. But if it were to happen, this is sort of, we're talking about a meter or less. But, we're predicting at least a meter contribution of sea level from Antarctica with these new model physics just from Antarctica, ignoring what Greenland's going to do, ignoring ocean warming. So obviously, we're thinking that the IPCC estimates of future sea level rise could be very much on the conservative low end of things. Okay, so it's bad news at the business as usual kind of world we might head into, but we have a choice in terms of what future we're going to head into. So I'll stop there, and I hope we can have a lively little discussion now. Thank you.